Welcome to this video example. In this example, we're going to deal with what's called two-dimensional equilibrium, also known as Newton's first law in two dimensions. So here's the situation we're given. A tetherball leans against the smooth, frictionless post to which it is attached. In the original question, it has the figure, but in this example, we'll make the figure ourselves. The string is attached to the ball such that a line across the string passes through the center of the ball. The string is 1.5 meters long and the ball has a radius of 0.16 meters with a mass of 0.33 kilograms. So our first question is, what is the tension on the rope, given that the tetherball is currently motionless? So let's go ahead and set up our situation here. We have a pole, and as this is a tether ball, from the top of the pole we have a string. The string is connected interior to a ball, so the string connects to the ball's center. Here's the ball. Let's make the pole thick enough that it actually contacts the ball, since that's what the problem tells us. Okay, we're told that the string length from where it's attached on the pole to the center of the ball is 1.5 meters. We're also told that the radius of the ball, which would be this length here from the center to the edge of the ball, is 0.16 meters. Okay, so, yes, and the final thing we're told, shouldn't forget the mass here, is that the mass of the ball is 0.33 kilograms. That's the information we're given, other than the fact that the ball is motionless. That means that V is 0 and A is 0. This is important because it means that Newton's first law is in effect, which means that the sum of all forces in the x dimension must be 0, and the sum of all forces in the y dimension here must be 0. So given this situation here, we can draw our force diagram for the ball itself. So we'll just make a little dot to represent the ball. We know that it's feeling the force of gravity. We know that it's feeling a force of tension from the string, and it is resting against the surface of the pole. And so we actually have a normal force here. Remember that the normal force is always 90 degrees to the surface of contact. So in this case, the normal force would be pointing to the left. So this is our normal force. It's important that this normal force be here in order to have the situation of the forces, the net forces, coming out to 0. If you imagine no normal force here, you can see that there are two components to the tension force. There's a vertical component and there's a horizontal component. The vertical component of the tension is in the opposite direction from gravity, so those two forces can potentially cancel out if they have the same strength. However, if we did not have the normal force, we would see that there would be no counteraction to the horizontal component of the tension force, meaning that the ball would have to be accelerating to the right. As it's not, we know that there must be some counterforce, at least one, that goes in the other direction. And in this case, this is the normal force, caused by the fact that the tether ball is in contact with the pole. So here is our force diagram for the tether ball. Now, the question is, how do we find the components of the tension first? Because we know that the normal force is all in one dimension, it's to the left, and the force of gravity is simply down. The only force that is in two dimensions at once is the tension, so we need to separate it down into its components. To do this, we're going to need essentially an angle. Either an angle here, or we could alternatively write the components like this and find the angle here. Either angle will suit our needs. Let's have a look at the original figure here. Here we have what's essentially a triangle that looks like this. It's a triangle that has the hypotenuse length of 1.5 meters, and the lower leg here has a length of 0.16 meters. The tension is along the string. So essentially, both of these triangles, this one here and this triangle here, are going to have the same angle here. This one. I'm going to make it a little thicker there so you can see. That's the same angle. So if we find the angle for this triangle, we can use it for this triangle. So let's think about our trigonometric functions here. We have a hypotenuse, and we have the length of a side that's adjacent to this angle. In other words, we could use that the cosine of the angle we want, we'll call it theta, is equal to the adjacent side, 0.16 meters, divided by the hypotenuse, 1.5. So, if we do this division here and take the inverse cosine, what we'll end up with is an angle of 83.88 degrees. So that becomes this angle here. That's the angle that we can use to find the components of the tension force. For example, we know that the sine of theta for this triangle here is equal to, well, the opposite side here for this angle is the vertical component of the tension, Ty, divided by the hypotenuse, which is the full tension force, T. Similarly, cosine of theta is equal to the horizontal component divided by the full tension. So now let's go ahead and solve. In order to do this, we need to make one final observation here using our force diagram. The sum of all forces in the y direction must be 0. We've already established that. And there are two forces in the y direction, one of which we can already calculate, that being the force of gravity, because we have the mass of the ball. In other words, the sum of, if we consider up to be the positive direction, positive Ty minus the force of gravity must be 0. The force of gravity is equal to the mass, 0.33 kilograms, times the acceleration due to gravity, 9.8 meters per second squared, and that gives us the force of gravity of 3.23, there we go, 4 newtons. That is the weight of the ball. So since there are only two forces acting in the vertical direction, they must be equal and opposite. That means that, oh, and I should state, let's just be careful here. This is a negative 9.8, so we end up with a negative force here. Okay. Remember that the gravity force here is negative in direction. Okay. All right, so the vertical component of the tension must balance out the weight. So it's going to be positive 3.234 newtons. So that gives us Ty. So now we can solve for the full tension force using the sine relationship up above. In other words, the tension force, full tension force, is equal to the vertical component of the tension divided by the sine of the angle. That would be 3.234 newtons divided by the sine of 83.88 degrees. And that yields a full tension force, again, now just rounding to 3 digits, 3.25 newtons. So that is our tension force for this particular situation, just done by recognizing that Newton's first law is in effect. All right, let's go on to the second part of the question. What is the force that the pole exerts on the ball? In other words, looking back at our diagram, what is this normal force here that comes from the fact that the ball and the pole are in contact? Well, we've already used the fact that the forces in the y direction must cancel out. Now let's use the fact that the forces in the x direction must also cancel out. That means if we consider the right to be the positive direction, positive Tx minus the normal force must be 0. In this case, we can again find Tx by looking at the trigonometric function. This time we can use the cosine one. We have found the full T tension force in the previous part, so we can use that now. That means that Tx is equal to the full tension T times the cosine of our angle. In other words, 3.25 newtons times the cosine of 83, right up here, 83.88 degrees. We put that in, we should get something around 0.345 newtons. And by Newton's first law, we know that the normal force here must have the exact same strength in the opposite direction. So this gives us our second answer. This is the same strength as the normal force, just in the different direction. So all of this can be determined just by following the fact that Newton's first law works in both dimensions. So this concludes this video example. Thank you for your attention.